So let's take a look at these. If you haven't already, get them out. I just wanted you to find the scale factor. Yeah, it's not overly difficult. It said that the A is the original in every diagram or in every question, and B is the scale diagram. So this is an enlargement with a scale factor of 2. This one was a reduction with a scale factor of 1/3. No, you do not get another one because yours is on top of the computer stack right there. You don't need another one. You have one. And I'm pretty sure the thing you just grabbed was a physics book. You don't want that. Okay, so we've got 2. We've got 1/3. One's an enlargement, one's a reduction. This one is 1/2, and it's a reduction. This one's 3, and it's an enlargement. Flip the page. I'm sorry, I should ask. Does anyone want me to explain how any of these were done? I mean, if you were here, I think it's fairly straightforward. If you were here paying attention and trying, it's relatively straightforward. If you were here, weren't paying attention, and were not trying, then I will not answer it for you. You can figure it out on your own. The scale factor here is 4. It's an enlargement. The scale factor here is 1/6. So it's a reduction. Questions, comments, concerns about either of those? Cool. And then the gingerbread man from Shrek. This is an enlargement, a terrifying enlargement. The scale factor is 300. It is 300 times bigger. Aren't you a basketball player, Marcus? In the middle of a season?
Yeah.
And your breakfast is a bag of sweet chili heat?
I already had breakfast.
Okay. Second breakfast is a bag of Doritos?
Yeah, I got them.
Okay. Fair enough. Okay, you may. I got one left. And it's sort of sharp. There you go. Okay, here we go. So. No, I don't want to see a fight. No fights. No fights. Okay, so. Let's take a look at this page here. Let's crank this guy out. It's a warm-up looking at scale factors. We want to find the scale factor of the original. The original is always the left one or the top one to the scale diagram, which is the right or the bottom. Some of these are fairly straightforward. We can crank these out relatively easily. As a class, what's the scale factor here? If you recall, which we're not recalling, the scale factor is defined to be the diagram length divided by the original length. I'm abbreviating everything. SF stands for scale factor, and the fraction is the scale diagram measurement divided by what the original measurement is. So if I look at something like this, these two triangles here, and we're told that the left is always the original, the scale diagram is always the one on the right, what's the scale factor for this scale diagram? It's 2. Because which lengths did you look at, Marcus? You looked at 6 and 3, okay. So the scale factor here is, you said that this side was your diagram divided by the corresponding side on the original. And 6 over 3 easily simplifies to 2. What we're going to start doing is we're going to start looking at shapes, I think it's today, where we have some sides on one diagram, and we don't necessarily have the corresponding sides on the other one. So if I look at a question here like 2, there's a set of sides I have to use. What sides are we going to compare here with number 2? Sorry? Yeah, the bottoms. We have to use the bottoms. Because I don't have, the top is going to be the same here, because it's a rectangle. But I can't use this right-hand side because I don't have the corresponding part to it over here. So I have to use these two. So what's the scale factor going to be here? Even just give me the unsimplified fraction. Sorry? How'd you do that? You put 25 over 10, and then you divided both of these by 5. And you got 5 over 2. Love it. In question like a thing like 3, what sides do we have to use here? Sorry? We have to use these left ones, that guy there and that guy there. So then we're going to have a scale factor that's going to be, and again, we always put the scale diagram on top. So this one's going to be 48 over 40. And then both of these are divisible by what? Are they? Okay, so if I divide them both by 8, 48 divided by 8 is? It is, you are right, Krishan. It is 6. And 48 divided by 8 is 5, so there's our scale factor, 6/5. Kind of a gross scale factor, but a valid scale factor nonetheless. Sorry? No, it wasn't for me. So for each one of these, we want to use sides that have a corresponding part to them. And then we can start to use this scale factor to fill in missing ones. Do we need to do the rest, or can we move on? Okay, Marcus says we're good, so let's flip. Let's take a look at this stuff today. So yesterday we represented scale factors as fractions. We could also represent them using other notation, a colon, for example, which I think I showed you guys this yesterday. And the way it's written, it looks like this. The size of the scale diagram, and then the colon, and then the original size. So effectively what we're doing here is we're taking this fraction and we're writing it as a ratio. Just so I know, hands up if you've seen this notation for writing a ratio in middle school. You're supposed to. Okay, cool. So whenever you've got a fraction like this and you want to convert it into a ratio like this, the numerator becomes the thing that's listed first and the denominator is the thing that's listed second. Like there is still an order to these things. So this thing becomes the scale factor is equal to the diagram, and we'll write it as a colon, to the original. And this is what the ratio is going to look like here. It's the same idea. So for example, this is a question we did yesterday. We had the two cars. One was 3, one was 15. When we wrote them as a fraction, we said that the scale factor it's always the scale diagram divided by the original length. So this one's going to be 3 over 15. Because the diagram length goes on top, the original length goes on the bottom of the fraction. This thing would reduce to a fifth, yeah. So when you write it as a ratio, it looks like this. The numerator becomes the thing that gets listed first, the denominator gets listed second. So this is 1 to 5. So it means 1 centimeter on the drawing is 5 centimeters of original size. This is commonly seen on maps. So I don't know how often you guys play with Google Maps. I don't know if that's still a thing. It used to be a thing. You play with Google Maps? Let's play with some Google Maps. Why not? Come here. Why aren't you working? It is the Abbey Senior Field again. We don't have to use the Abbey Senior Field. Where do we want to use? Do we want to use something more interesting? Costco?
Oh,
why Costco?
Near my house.
Are we near your house? I know there's a lot of things that we're near right now in this diagram. We're near Tommy Gunn's original barber shop too. Now you can see your house? Oh yeah, it's right up here somewhere. In this gigantic square on the north side of the river. So these things, maps like this, also have a scale. It's not written the way we're used to seeing, the way that I'm showing you how we're seeing it. It actually, I don't know if you ever looked at it, but guy down here. And what this is telling you is that this length right here is 2 kilometers on the real one. Often maps will have it written the way we have it written. This one obviously doesn't. This one was, so that would be whatever this length is. Then as we zoom, the scale changes. So now this is getting larger as we zoom in. 2 kilometers looks like a larger line. You want the Costco? There's a Costco. It's oh, yeah, it is up. That's my road. There's Costco. How did I just find it? Oh, that's my road down there. Also says Costco also. So we could, you want a field trip to Costco? I feel like I would want to be responsible for all you. IKEA is a fun place. I got kicked out of IKEA once. We're playing hide and seek. You don't like it when you play hide and seek. They really don't. Okay, so the question that we're looking at, there's the Abbey Senior Field right there.
Why is it so black?
Why is it so black? Because of the turf field. All those little rubber black pellets that you guys bring in every day after lunch when you hang out on the field. Not you walk. I don't know. I see it on the side of the class when you guys are out there. As you guys walk on the field, it brings up those pellets. But we've got a scale here. It is whatever this length is, I want to measure it on the TV.
It's 10 meters away from us.
Oh, it's not 10 meters away from you. That's not how this works. So on this particular diagram, as it's drawn, that is, if we measure it on the TV, that is 1, 2, 3, 4, 5, 7 centimeters. 7 centimeters on the television. Yes, it would be, but it's a smaller picture on the computer. So, but you guys are looking at the TV, not my computer monitor. So 7 centimeters on the TV is 10 meters in real life. And so we can start to draw some of these, like measure some of these things up. If this length here is, what is that? 34 centimeters. How wide is the field? Because what we've got, I'm sorry?
5.
Why would you say 5?
They said 5.
Don't listen to the girls. You weren't here. The attendance question was, what is one of your pet peeves? And one of those girls, these guys all blamed Gabe as one of their pet peeves. But one of those 3 girls said you were their pet peeve. So I would just not listen to any of the 3. This guy's dead. Okay, so we've got the field. The field looks something like this. We're told that 7 centimeters on the map, on our scale diagram, is equivalent to 10 meters in real life. So our diagram comes at the beginning of our ratio. The actual length in the real world comes next. These should be the same units though. So 7 centimeters, 10 meters is times 100. 1,000 centimeters. So if we're told on this diagram, what did I say it was, 34 centimeters? We can start to use this scale factor to figure out what it's going to be on the original. What is it going to be? 7. Well, let's take a look. Let's make it more interesting. Okay, back to this. Here we go. Why would I do that?
It's like the biggest school.
Okay.
It's 177.
So, maps have a scale factor that tells us how much the map was reduced. So here's another version of that same map. It's hard to see here, but there it is. The distance between the goalposts on the map, if we measure this out, in this version of the map, the distance between A and B, it's not actually 10 centimeters, it's 9.5 centimeters. 9.5 centimeters. It would have been easier if it was 10. Let's just round that to 10. Let's go back and round that back up to 10 to make our life a little bit easier. So then to find the scale, the real distance between the two goalposts is 11,000 centimeters. 11,000 centimeters, just, you know, for all you football players out there, is 110 meters. So then what's the scale factor going to be for something like this? Well, it's always the original over, sorry, it's always the scale diagram over the original. Scale factor equals diagram over original. So the diagram here is 10 centimeters over the original, which is 11,000 centimeters. So if we reduce this thing, it's going to become 1 over 1100. Or if I write it as a ratio with the colon, it'll say that 1 centimeter on the paper is equivalent to 1100 centimeters on the field. It is a lot of centimeters. It's 11 meters. It's also a lot of meters. It's true. Very insightful this morning, Hayden. What would happen if you did what? That would, I'd have to send you to the hospital, almost certainly. Don't try it. Don't listen to the people. Okay, flip the page. Okay, crank out the scale factors. All we're doing right now is cranking out these scale factors. On your mark, say giver. The left is the original. The scale diagram is on the right. Crank out a bunch of scale factors for me. That's all you're doing right now. Get to work, Raven. I just want you to crank out a bunch of scale factors for me. Then we're going to go ahead and start using them. You're just using the fact that the scale factor is equal to the diagram over the original, or as a colon notation ratio, it's diagram to original. You're just going back and forth between, that's all you're doing. It is easy. You're just getting a handle on how to use that notation. And then we're going to go ahead and we're going to actually start using these things to calculate stuff. Finish this first. And make sure you don't forget your notes this time. Just say you're ill sick. Just say you're sick. Are you guys done?
Yeah,
I believe you are. Hayden, are you done? Have you started? Okay. Okay. Sweet. Keep going. Not hard. Crank them out. Yes. Sorry? Nope. Don't do it. I will call poison control. Don't do it. Sorry? Yes. This page and the next. Page 3 and 4. Yes. And we are going to do lesson 3 today, too. It's only 10 to 9. We have 40 minutes. We're going to make it more interesting. Okay, are we done? You did this page and this page? Yeah, let's crank them all up. In 3 minutes, we're going to go over the answers to these. Hayden, get your stuff done. No, that's what we're going to do next.
Like tomorrow?
So like in 3 minutes.
Okay.
Okay.
5 over 15.
So we're going to get kilograms. So it's 2 over 7, makes it 2 to 7. So 6 over 30, which makes it 1 over 5. That's 1 to 5. Let's do 1 over 11. Yes, are you done? Okay, go ahead. Oops, I oops this. I did it backwards. 11 over 1. 11 to 1. 20 over 3. 22. Okay, Hayden, go put it in the garbage. Okay, thank you. Okay. Okay, here's the first page. Comments, questions, concerns on any of those? Let's get them done so we can go use them. I oops one of them. Okay, going once, twice, thrice, sold. Okay, flip the page. These ones. Let's go 40 over 10, which makes this 4, which makes this 4 to 1. We're going to go. I'll go 18 over 3, which makes this 6 over 1, which makes this 6 to 1. This is going to be 3 over 42, which makes this 1 over 14, which makes this 1 to 14. This one's going to be 42 over 7, which makes this 6 over 1, which makes this 6 to 1. And then this guy here, the Stickman, Sam, Raven, and Dokran is 14 centimeters tall on the phone screen, but in real life, he is 154 centimeters tall. What is the scale factor? So these ones, the order here is going to be slightly different. The diagram, again, goes in the numerator. The actual height goes in the denominator, and that thing is going to be reduced. Believe it or not, both of these are divisible by 14. So that's going to be 1 over 11, which is going to make this thing 1 to 11. 1 centimeter on the phone is really equal to 11 centimeters in real life. And then there's a soccer pitch. The actual measurement of the width is 60,350 centimeters. On the map, the field is 17 centimeters. So it's always diagram over actual. Believe it or not, both of those are divisible by 17. So that's going to be 1 over 3,550. So 1 to 3,550. And what that means is 1 centimeter on the map is equal to 3,550 centimeters in the world. Okay, so let's actually start using this, shall we? Flip the page. There we go. So, similar figures, we talked about this a little bit already. Similar figures, shapes, objects, diagrams, etc. have a few things in common. They have to have the same shape. That's the easy part. But they can be different sizes, enlarged or reduced. All parts must have the same scale factor. Things can look similar, but if the scale factor is slightly different or radically different, those shapes cannot be considered similar. So I've got some examples here. These are exactly the same diagram. One's just been shrunk. These are the same size. These are the same diagram. This one's been blown up. So these are all considered similar. These are not. These two are obviously different pictures. These triangles are different, and if we looked at the scale factors, we'd see that too. And those aren't even the same object. So similar figures are, excuse me, enlarged or reduced by the same scale factor. I don't know why there's a blank here. That's not overly complex. This means that every dimension is proportionate. So if we start looking at some of these sides, this side here, we'll call it side AB, it's the side that joins those two corners together, is similar to what corresponding side on this shape? RS. So then BC is going to be similar to what corresponding side on this triangle? ST. And then CA is going to be similar to what corresponding side on the other triangle? TR. And we can start using this information to start doing some calculations, because we haven't done any of that yet. What kind of math class doesn't have some calculations in it? Here we go. So, if we look at the left sides here, we've kind of done this already. We're just reviewing something we've already looked at. If we look at the sides here, the small rectangle is 2. If you think now is a good time to go to the washroom, Raven, go ahead. This after that works too. The scale factor here, again, if we take a look at what's going on here, let's call this the diagram. Let's call this the original. The scale factor then, if I'm looking at this left side, the corresponding side is this 8 centimeter side. So then the scale factor is going to be 8 over 2, which I can simplify to 4 over 1. If we look at the top piece, the left one is 10 centimeters. The right one is 40 centimeters. And so when I'm looking for the scale factor there, it's going to be the diagram over the original. This thing also reduces 40 over 10. Both of those are divisible by 10. It's also going to reduce to 4 over 1. We have the same scale factors. And so what this means is it's an example of the truth I just said on the other page. All corresponding parts are proportional. Means they have the same scale factor for each piece. What that allows us to do is it allows us to do two things. It allows us to go ahead and start checking, well, are these diagrams similar or not? And if they are, can we find missing links? So let's take a look. I've got two diagrams here. I've got this and I've got an actual box. Let's figure out if they're similar figures. So this is going to be our original. This guy over here is going to be the diagram. And let's take a look and see if we've got, to see if they're similar, they need to have the same scale factor. So we're going to compare the dimensions on the right with the dimension on the right, and then the dimension on the bottom with the dimension on the bottom. So the scale factor here is going to be 3 over 18. Compare the one on the right with the one on the right. And it's always diagram over original. So then 3 over 18 is going to reduce to what? Yeah, 1 over 6. To see if they're similar, we need to make sure the other dimension follows that is equivalent, right? So if I want to check the other one now. The bottom piece on the diagram is 2. The bottom piece on the original is 12. What does 2 over 12 reduce to? Yeah, both of them are divisible by 2. Divide by 2, divide by 2, it's going to be 1 over 6. These are the same scale factor. These two are similar. Let's go look at the next one. This one's got, the arrow there tells us the direction that we're going here. This is the diagram. This is the original. And we want to go ahead and we want to take a look at, why do you have the chemical package now? Yeah, why do you have it? Okay. We want to see if these two are similar. Do they look similar? Andrew says they do. Does anyone disagree? Gershon says no, they are not similar. Why do you say they don't look similar? Oh, no, you're actually doing the math. Just looking at the picture, Andrew, you looked at the picture and said, yeah, they look like they could be close. Gershon's like, okay, let's go ahead and do the math. So let's go ahead and do the math. To be similar, they have to have the same scale factors for the corresponding parts. So the scale factor, if I compare the bottoms, remember scale factor is always diagram over original. So it's going to be 10 over 2. 10 over 2 reduces to, both of those are divisible by 2. 10 divided by 2 is 5. 2 divided by 2 is 1. So if I look at the bottoms, the scale factor is 5. let's look at these two. The scale factor for the right slant, it's always diagram over original, so it's going to be 42 over 7. 42 and 7 are both divisible by 7. So that's going to give us a scale factor of 6 over 1. Are those the same scale factor? Is 5 over 1 the same as 6 over 1? All of you should just very easily say no, or maybe we're so bored it's hard to tell. Gershon, you're right. So even though Andrew, you did a quick look, yeah, they look similar. Are they? No. They're very close. Because these two are different. These two shapes cannot be considered mathematically similar. We can actually go back and answer this. These are similar in the first one. When we're given more than one dimension, we have to check all of the dimensions. So I've got something like these guys down here. If you just glanced at those, what does your gut tell you? Are these similar or not?
Yeah.
They look like they could be. But your gut says because this is a math class and Dawidoff's out to get me, it's probably not going to be. You done the math already? Which one's the problem? The 10 to the 40 is something else. So if you do what Gershon is doing and you pick your sides carefully, you can get it. If you're not careful and you just go ahead and crank them all out, if you don't stop to think about what you're doing, then you do have to check them all. But let's take a look. You're suggesting if this is the diagram and this is the original, Gershon, you said if we look at one of these, if we look at these two sides, this one's going to be 6 over 3, which reduces to 2 over 1. But if I look at these two sides, one of those scale factors is not going to be, one of these is not like the other. So this one's going to be 40 over 10. We're going to divide both of those by 10. So that's going to give us a scale factor of 4 over 1. So just by picking two good sides, we can see that, in fact, Gershon, you're right. These are not the same. If you're not careful, though, let's take a look at some of the other sides there. If I take a look at this guy and this guy, the scale factor there is going to be 56 over 14. Both of those are divisible by 14, believe it or not. Divisible by 14, divisible by 14. 56 divided by 14, does anyone know? It's 4. So this one's also going to be 4 over 1. So then let's check the last two. Well, that's the same. The scale factor there is also going to be 56 over 14. So that's also going to be 4 over 1. If you're not careful, if you picked two other sides, you'd be like, oh yeah, they're the same. In fact, 3 of the sides all have the same scale factor. It's this last little piece here that's not. So if you, like Gershon, picked well to start, you could have stopped right here and said, okay, well, I'm done. These are not similar. But if you don't stop to ask yourself the question, what good sides can I pick here to compare and to prove, then you got to check them all. So let's take a look at these last ones, or this last one. Are these two similar? Do they look similar? Yeah, they look similar. Let's prove it. You there? You've done the math already? Okay. The scale factor for each one is 9. Okay. So which you called this one your diagram? And this one your original? Okay. So if we look at this guy and this guy, 7 over 63, both of those are divisible by 7. It's going to be 1 over 9. Cool. Let's look at these two. I got 10 over 90 reduces to 1 over 9. Sweet. Let's look at these two. 4 over 36 reduces to 1 over 9. The quicker you are at being able to reduce these fractions, something that you did in middle school and we reviewed way back in the second week of September, your life's going to be a lot easier. And then there's this last one. You might need a calculator for this last one. It's going to be 14 over 126. Or you can just start dividing all of them by, let's divide by 2 and 2, just to make my life a little bit easier here. That's going to be 7 over 63, which we've already seen reduces to 1 over 9. So you bet. Juno did the math. But if you tell me that they're similar, you've got to be able to prove it. Not similar is easy. Proving something isn't true in math is easy. Find me one example where it breaks. But telling me that something is mathematically true, you have to check them all. Flip the page. If we know that two figures are similar, then we can use scale factors and some relatively simple algebra to find unknown dimensions. Recall, if I set something up like this and I said, okay, well, I know my scale factor is 1/3 and this is equal to something I don't know over 9, how do I find that unknown x? Well, I'm isolating. I want to get x by itself. What am I doing to the x right now? Do you know? Yeah, I'm dividing by 9, so to get it alone, I want to multiply both sides by 9. You betcha. So on the right-hand side, my 9's cancel, and I'm left with just the x. On the left-hand side, how do I multiply a whole number by a fraction? You put the whole number over 1, and then you multiply the numerators, multiply the denominators. So this thing's going to become 9 times 1 is 9. 1 times 3 is 3. So this is going to become 9 over 3, which reduces to, what's 9 divided by 3? 3. So what that means is x must be equal to 3. If the unknown is on the bottom, we've got two ways that you can solve something like this. We've got 1/3 equals 5 over x. One way to do this is to say, well, okay, I want to get x alone and I want to get it up in the numerator, so I can multiply and divide to isolate the unknown. So what I'm going to do is I'm actually, to get it up and alone, I'm going to multiply both sides by x to cancel it on the right. And so I'm going to get x over 3 equals 5. And then to get x alone, now that it's in the numerator, we can multiply both sides by 3. On the left, they cancel. Hayden, if you don't care to be here, you can go out and sit on the couch. So then 5 times 3 is 15. So then if this ratio is true, 1 over 3 equals 5 over x, x must be equal to 15. That's one way you can solve these things. But when you're dealing with two simple fractions like this, and this all we're going to be doing is dealing with these simple fractions, there's actually a step that you can take first. Instead, what you can do is, if what you're looking for is in the denominator, you can flip both fractions. So what's that going to give me? On the left-hand side, I'm going to get 2 over 7 is going to equal x over 4. If I flip one of them, I have to flip the other one. And now the thing that we're looking for is alone in the numerator. Taking the reciprocal of both sides is a valid mathematical operation, and that's what we've done. And now to get x by itself, all we have to do is what we did up here. Multiply both sides by 4. On the right, they're going to cancel because I'm multiplying and dividing by 4. And what I'm going to get here is that x is going to equal, put the whole number over 1, multiply my numerators, multiply the denominators, it's going to be 8 over 7. You are allowed to have fractions for things like this. And so where this becomes useful is things like this. Here are two triangles. I'm telling you that they're similar. What's the missing side? And so if you know that they're similar, this guy here telling you that they're similar means, let's go over here, they're going to have the same scale factor everywhere. And if it doesn't tell you that which one's the original, which one's the diagram, you can choose. To make your life easier, whichever one has the unknown, call it the diagram. Because the diagram always goes in the numerator. It's going to put your unknown in the numerator. And call this one your original. So if the scale factors are the same everywhere, that means that this side divided by this side, 3 over 12, the scale factor that links these two, is going to be equal to the scale factor that links these two. And remember, scale factor is equal to a diagram length divided by an original length. So our unknown there is going to end up in the numerator, x over its corresponding side in the other one. And so if these two triangles are similar, this is what we need to solve to figure out what this length is. This is not overly difficult to do. To get x by itself, I'm going to multiply both sides by 20. On the right-hand side, they cancel, leaving me with x. And I'm going to put the whole number over 1, multiply my numerators, multiply my denominators. And we're going to get that x is going to be 20 times 3 is 60, 12 times 1 is 12, and 60 divided by 12 is what? If you need to use a calculator, you're welcome to use a calculator. If you've got the times tables memorized, 60 over 12 is 5. So what that means is this side length must equal 5. If you go the other way, if you call this, yes, Juno?
So I did that. It's just like 12 and 20 were in the same fraction. It would be 12 over 20
So you use sides within the same triangle. I'm just trying to think of an example where that may not work. While what you've done is also true, it uses a property we're not going to talk about. So your question is, does it work? Yes. The short answer is yes. I would encourage you to connect it to scale factor like we've been doing. So to connect them across between the two triangles is going to make your life more consistently easier long term. But what you're doing will work. Yes. Okay. I'll do 2 more examples. and call it a day. Let's find the missing sides of the following similar figures. Yes, I know we only have 15 minutes. I know. So here's what's gonna happen. I'm gonna finish the lesson. I'm gonna say there's not gonna be any homework, and tomorrow when I'm away, you guys are gonna have a bunch of questions to practice. But you're getting Mrs. Reed, who's a math teacher who's been here before and quite likes helping you guys. I already know she's my TOC for tomorrow. So that's what the plan's gonna be. So let's take a look at this. 2 more examples, same kind of thing. What we wanna do is we wanna find the missing sides. I'm telling you that these are similar. The only weird thing is, in all of the other examples that we've done, they've been oriented the same way. These are not. They've been spun. But there's notation there that does kind of give you an idea of which sides correspond, right? So if you look here, this corner has 1 slash through it. This one down here has 2 slashes through it. This one over here has 1 slash through it. This one over here has 2 slashes through it. And so what that means is these 2 corners correspond to each other. And these 2 corners correspond to each other. And so it starts to give you what sides are going to correspond even though these triangles have been rotated. It's going to tell you that side AC, this guy here, which conveniently has the unknown, is going to correspond to the same side. So AC here is going to correspond to PQ here. Even though we've rotated them, because there's notation within the triangle, we can use the notation to tell us how they're oriented. And in fact, in this question, there's 2 unknowns. We don't know C on the big one, and we don't know D in the little one. So we're going to have to go find this thing twice. So again, it doesn't matter which one you call the diagram and which one you call the original. It's just going to change where you place the variable in the fractions is all. So if I'm working left to right again, let's call this one the original and this one the diagram. And if I want to find C, what we're going to do is we're going to set up the 2 equivalent scale factors. Put your phone away, Hayden. We're going to get 4 over C, because these are the corresponding pieces. C, not 6. 4 in the diagram over C in the original is going to equal. Now, what sides can I use to help us out here? These 2 are going to correspond. What other sides correspond? The 10 here and the 5 here correspond, and I know both of those values. So if these 2 correspond and those 2 correspond, what that means is these 2 must correspond. So to find my unknown here, I can't use these bottom 2 because there's another unknown in there, but I can use these green ones, the 10 and the 5. So if I got 4 over C, that's going to equal 5 over 10. And so now I can go ahead and solve these things. I could multiply the C up and then solve, or the simpler technique is just to flip both fractions. This one's going to become C over 4 equals 10 over 5. And now to solve this thing, I'm going to multiply both sides by 4. This is going to become 40 over 5, which is 8. So what that's going to tell us is that side C here is equal to 8, whatever units are, centimeters, meters, I don't know. And now I can go ahead and do this last piece. Hey, Hayden, you shouldn't be speaking right now about anything not math related. So I can set up the same one here, diagram, original. I want to find D now. So I'm going to get D over 6, because these are the corresponding sides, are going to equal, let's go back and use these green ones, 5 over 10. To get D alone, it's already in the numerator, so there's no flipping I have to do. I'm going to multiply both sides by 6. On the left, they're going to cancel. On the right, I'm going to put the whole number over 1, multiply numerators, multiply denominators. I'm going to get 30 over 10, which is 3. So C is equal to 8, D is equal to 3. I found telling you they're similar, it telling us they're similar, we can find both of the unknown pieces. Okay, Juno, this is what you were doing. Here we go. One last example. I've got a different situation here now. I've got a small triangle where I don't know anything, and a big triangle where I know 2 of the sides. If I tell you that the original triangle is enlarged by a scale factor of 4, so in this case we're given the scale factor here, and given the scale diagram on the right, we want to find the unknowns in both of these. This is actually fairly easy. I was wrong, Juno. This isn't what you were doing. For something like this, we're given the scale factors. If we know the scale factor, then we can use the scale factor to find the unknown dimension. If to go from y to 16, I blew this thing up by 4, how am I going to go the other way? We're going to divide. We're just going to do the opposite. Going this way, we multiplied. So going this way, we're going to have to divide. So then what this means is that 4 times y equals 16, because I blew this thing up. So I'm just going to divide both sides by our scale factor. And we're going to find that the side length y has to be what? 4. So then likewise, I don't actually need to write out, or maybe it would be useful to write these things out, but the algebra is fairly simple. If this side length here is 8, and the scale factor is 4, given that the scale factor is 4, what does x have to be? Sorry? 2. Because if I divide both of these by the scale factor, x is going to have to be 2. So you can use the scale factor directly as well. And that's it. So, I know there's only 6 minutes left. What I'd like you to do today, just to get a handle on practicing these things, I want you to use the next 5 minutes. I just want you to do question 1 and 2. That's it. Do questions 1 and 2. Shobit and I can help you out in the 5 minutes that remain. And then tomorrow you're going to spend the rest of the time playing with these in more detail. Delete. Okay. Yeah, man.
Why don't you just look at the other numbers and then just do it? Like if you know 10 or 5, if you know that's just time multiplying it by 2, what's the point of doing all this work when you could just multiply it by 2 and do that?
As long as you've got a method to show me, that's fine. Because not everyone's going to see it as quickly as that. So if you've got a method that works consistently, that's, yeah. Not a chance. Okay.